Welcome everybody. Let's continue with our lecture 9, Dantzig-Wolfe Decomposition and numerical example portion. Here we have example problem as minimization of negative x1 minus 8 times x2 minus 5 times x3 minus 6 times x4. And we have a two set of constraint S1 and S2. And S1, we have two set of constraint A1 and A2. And A1 is one single constraint. We call it, refer as a global constraint or call it a difficult constraint. Because if we involve this constraint, actually all the variable has to be involved, x1, x2, x3, and x4. And this variables, this constraint is x1 plus 4x2 plus 5 times x3 plus 2 times x4 plus s1, which is my slack variable, and make it equals to 7. So we call that a1 hat times x equals to b. My a2 hat times x equal to b2 and can be separated into two sets. The first two constraints in the A2 involve only variable x1 and x2. And the second set of A2 constraint only involve variable x3 and x4. So this is a fairly standard situation, what we can do. So we can write out S1 and S2 separately as only involve part of the decision variable. One only involve x1, x2, and the other ones involve x3 and x4. That's a typical structure we dealing with using Dantzig-Wolfe decomposition theory, decomposition algorithm, and this is also we show you in the algorithm how we start generating columns, and each column represents a extreme point of my feasible region. I can plot, since there are only involving two variables in each one of the subproblem, and we can do x1 and x2, and we can easily see the extreme point, visualize the extreme point for the first subproblem S1 and the feasible region for S2 in that case. Okay, so if the worst comes to worst, we can actually come back here to find out what is my optimal solution graphically. So initial basic feasible solution, what we find is we're going to use 0, 0, 0, 3. Okay, so the first two, x1, x2 equals to both equal to 0. And x3 equals to 0 as well, x4 equals to 3. In that case, I can forming, I can forming the S1, okay, equals to B1. S1 is my slack variable for the global constraint, equals to B1 minus P11 minus P12. So equals to 7 minus 6 actually equal to 1. So what is P11? P11 is the A11 portion times X11 only involve X1, X2 equals to 0. P12 is equals to A12 times X12, which involve only X3 and X4 equals to 5, 2 actually times 0, 3, which 0, 3 is the current constraint. If you go back to the previous slide, we can see, okay, the first two coefficients 1, 4, and the second two coefficients 5 and 2, which is if I separate them out as x1, x2, x3, x4. Okay, easy. The C transpose times X, if we separate X1, X2, and X3, X4 are two separate blocks, we can calculate separately. C1 times X11, C2 times X12 equals to 0 and negative 18 correspondingly. Therefore, we can write out my master problem. Looks like this. Okay. Minimization of F11 times alpha 1, F12 times beta 1. And instead of using lambda here, we're using alpha beta, representing the two separate blocks of subproblem. Okay. Equal to 0 times alpha 1 plus negative 18 times beta 1. Of course, this is my global constraint after conversion, and alpha 1 and beta 1 initially has to be 1. Why? Because there's no alpha 2, there's no beta 2, only one single extreme point to start the basis. Okay? So I also show you how the 0 and 6 calculated in the global sense and why the S equal to 1. S1 equal to 1. My slack variable for the global constraint currently equals to 1. For that, my basic variables currently for my master problem will be my slack variable, which is equal to 1. And alpha 1 is my the convexity weight for the first part of the subproblem. And the beta 1 is the convexity weight for the second part of the subproblem. So my corresponding B matrix is corresponding to S1, alpha 1, and beta 1 column. So S1 is for the global, equals to 1, 0, 0, 1, P11, and P12. And the second set of second rows of B equals to 0, slack variable involved, alpha 1 equals to 1. Okay? And the third row represents only beta 1 involved in that equation if we go back to look at the master problem. Sorry. Oh. Sorry. If we look at the S1 portion, okay, S1 alpha 1, beta 1, correct? So in S1 column is 1, 0, 0. And alpha 1 column is P11, 1, 0. Beta 1 column is P12, 0, and 1. And that's exactly what I have from here. Okay? Then once we have right here, this is my B matrix. I can calculate the corresponding B inverse matrix. Okay? Fairly straightforward. Negative 6 on the upper right corner. So now we can calculate our do variable. The do variable equals to CB transpose times B inverse. Okay, equals to CB equals to 0, 0, negative 18 for now. Okay, times B inverse equals to 0, 0, and negative 18. That's fairly straightforward. So I want you to take a look. This is my master problem. Again, okay, involving alpha 1, beta 1, and S1. So S1's coefficient is 0, so 0 times x1, 0 times alpha 1, but negative 18 times beta 1. And that's why the CB represented as 0, 0, negative 18. Okay, I want to make sure you understand where are all the variable numbers coming from. Again, to form the master problem, okay? And alpha 1 has a coefficient of 0 and the objective function. Beta 1 has a coefficient of cost coefficient of negative 18. And S1, since it's a slack variable, then I have a 0 coefficient as well, cost for the for the slack variable. Okay? Now for the subproblem, since I have two subproblems, we'll call it SP1 and SP2. SP1 only involve X1 and X2 right here. Okay? Involve one of the omega naught. Okay? And this portion equals to Zj minus Cj, omega transpose times A1 minus C transpose equals to 1 and 8 times X1 and X2 plus omega naught 1 equal to 0 for now. Okay, so my objective function is X1 plus AX2 as my objective function for the subproblem. And X1 and X2 belong to S1. Okay, first set of constraints. And the optimal solutions by solving this subproblem is X1 equal to 0, X2 equals to 2, objective function equals to 16. In a similar manner, we can solve the subproblem involving X3 and X4. And here we have X3 equals to 4 and X4 equals to 3, and my objective function value equals to 20. You see both of the objective function I have so far, they are positive. We know the Zj minus Cj, since our objective function is Zj minus Cj. And we know that's going to be, both of them can improve my objective function. And I recalculate the current solution, 0, 2, 4, 3, as those are extreme point in my feasible region. So I can recalculate P11, P12 using this formulation accordingly. And we can recalculate F11 and F12 by C1 times X11, C2 times X12. C1 is the cost coefficient corresponding to X1 and X2. C2 equals to the cost coefficient corresponding to X3 and X4. X11 is the 0, 2 we're getting from the subproblem, and 4, 3 are the optimal solution. I get it from subproblem 2. Once we recalculate these, we can reform our master problem. Okay, our master problem becomes the form we just calculated. Now you see we're using the revised simplex method. This is our original tableau. This portion is the B inverse. Again, and this part will be my omega 1 and omega 0. This is my objective function value. Okay, this is my objective function value, negative 18. These are the current basic solution with respect to the master problem, which S1 equals to 1, alpha 1 equals to 1, beta 1 equals to 1. Now we could have alpha 2 or beta 2 come into the basis. And which one to choose? Of course, we're choosing the bigger one. The 20 as one of my 20 is one of my entering. Between 16 and 20, I choose beta 2 first, okay, as entering. Then we can perform the minima ratio test on the last column. What do we do? Taking the right-hand side, A divided by 20 or 0 divided by 1, okay? I'm sorry, 1 divided by 20 and 1 divided by 1. I'm sorry. So this is your right-hand side divided by the entering column Y, okay? And therefore, of course, S1 is the one to leave the basis. So beta 2 coming in, S2, S1 going out, my slack variable going out. So we can recalculate the entering column. Instead of 2001, I'm going to, instead of A10, I'm going to using B inverse times the A10 right here. Still is A10. B inverse times B22, which is the other one. Then we'll have 2001 over here. Okay, these are how we come up with those. Again, after one pivot, I can, since S1 is leaving, so I'm going to make a beta 2 column, looks like 100, identity column, okay? We can still entering beta alpha 2 as well. So alpha 2 right now have a value of 8. So it still can be a entering variable in that regard. But once alpha 2 enter, and beta 2 will be the leaving variable based on the minima ratio test. Okay? So what we have is the right-hand side divided by this column. Okay? 1 divided by 1. 1920 divided by negative. So I don't care about the last one since it's a negative. So I only worry about the first two. And we figured out 1/8 is smaller than 1. So beta 2 is leaving. And after one more pivot, and alpha 2 becomes identity column. Okay, alpha 2 becomes identity column, and beta 2 has a value of a negative 20. Okay, and this beta 2 becomes a non-basic variables again. So my current basis right now is alpha 2, alpha 1, and beta 1. And I'm totally, the global constraint is in the equality format. So we can resolve the subproblem SP1 and SP2 again, okay, using the current solution of omega 1 and omega naught. And for the subproblem 1, I have a 0, 0 to begin with, x1, x2 on the second iteration. They both equal to 0, and my z, my objective function value, equal to 0. Solving the subproblem number 2 involve x3 and x4. We got 0 and 3, and the optimal objective function value for that subproblem also equal to 0. What happened? In this case, we know since the objective function value for either one of those basic subproblem, they represent the zj minus cj value for the master problem. So therefore we know, since they are either 0 or negative, and these we know is no point to entering anymore. So the current solution on hand is optimal for the master problem. All right. Finally, we're talking about the lower bound of the minimum cost problem. My objective function value, if we look at it, the due problem, equals to omega 1 times b1 hat minus sum of the omega zj. We can actually represent it by lambda ij, if that's the case, okay, lambda ij for all the extreme point we find. And the Fij minus omega 1, omega 1 transpose times Pij times Pij minus omega 0j, and that's the Zj minus Cj for my objective function. And look at this, if we put it together, equals the summation of negative lambda ij times zij minus cij, which is smaller than z, equals to zj, okay? It's greater than equals to summation of negative lambda j times zj, okay? So in this case, and that's going to be my lower bound. So my lower bound, actually, the minimization of the z, which is the global optimization objective function value, will be always greater than the due objective function from the due problem. And that's the solution we're going to have. And for the lower bound, we talk about more numerical example in the homework as well. So here we conclude this lecture. We introduce a so-called decomposition scheme, referred as a Dantzig-Wolfe decomposition. We separate our constraint into two separate sets. One we call it global constraint or difficult constraint. The other set we call it easy constraint, or we call it local constraint. Okay, we separate the global constraint and the local constraint separately. We try, because if we can ignore temporarily the global constraint, I can solve the local constraint with the separate variables and in the separate problem. Once we have solving each one of the small subproblem, we can combine them together and try to see the current solution satisfy the global constraint. If not, we adjust our due variables value and we return to our subproblem, resolve each one of the subproblems separately, and we combine together and we're trying to fit into the master problem, see if they satisfy the global constraint. If not, again, we adjust the due variables. Of course, the master problem, the decision variable is the convexity weight instead of x itself. So this kind of scheme is each time I find a extreme point from the subproblem, and then we feed that extreme point to the master problem. See how much the newly added extreme point weight to the optimal solution if they can find a region. So this is basically we still going through from one extreme point to another extreme point to another extreme point and see which one, the newly added extreme point, will provide a better objective function value. If we find an extreme point cannot improve my objective function overall, then I'm done. Okay, so we're going to conclude this set of lecture for lecture 9, and next time we'll continue with lecture 10 called interior point methods. Okay, thank you very much.